All right, guys, so today we're going to talk about chemical transformations. We've talked about 3 ways that chemical reactions can be driven, right? And so we're going to first go over the things that cause chemical transformation. The first one of those is solubility, right? So let's remember that in solubility, forming a precipitate, which is something that's solid that forms from 2 aqueous solutions, can drive a chemical transformation. So here we can recognize that we have a very long reaction, right? We've got sodium carbonate plus calcium chloride makes calcium carbonate solid, and then there's some sodium chloride left in solution, right? So we can remember, right, that when we form this solid from 2 aqueous solutions, that is a precipitation reaction, right? Precipitation. If we were writing a net ionic for a precipitation reaction, anything that says AQ becomes ions in solution. And the subscript will come out front, unless it's a polyatomic ion. So let's practice that with this one. We've got 2 sodium ions that are each a +1 charge. We also have 1 carbonate ion that stays CO3 because it's covalently bonded. Then we have this calcium chloride that's also aqueous. The calcium has a +2 charge, and there's 2 chloride ions that would be in solution. That's going to form calcium carbonate solid, stays solid. It is our precipitate, and it forms that white stuff that we saw in the lab. And then we have 2 sodium chlorides that are aqueous in solution. So that means we have 2 sodiums and 2 chlorides. So where would our spectator ions be? Remember that spectator ions are the ions that are the same on both sides. They aren't reacting, they're just watching the reaction, just like spectators do. So sodium's the same on both sides, and chloride's the same on both sides. That leaves us with our net ionic equation. Calcium plus carbonate makes calcium carbonate. And that's the only thing that's actually happening in the reaction. So remember that net ionics are kind of small, and they just take the thing that's solid and the 2 ions that make it up. Okay? Now let's talk about our next one. Our next type of chemical transformation we talked about was when we have an electron transfer. In an electron transfer, one element loses electrons. That's called oxidation. And another element gains those electrons. That's called reduction. So one clue that we have a redox reaction, right, is that we have elements. Let's just underline those words, right? There's got to be single elements, because elements in their natural state all have an oxidation number of 0. You'll be able to recognize a redox reaction because you'll only have elements on both sides of the equation, just like a single replacement reaction, right? And so those elements will change their oxidation numbers on one side of the equation to the other side of the equation. Okay? So let's write another net ionic equation for this redox reaction. Remember, anything that says AQ becomes ions in solution. Well, aluminum solid, that doesn't say AQ. And so I'm going to keep that as Al. But CuCl2 says aqueous after it, so that copper is a +2, and the there will be 2 chloride ions in solution when we dissociate this copper 2 chloride right here. Okay? That's going to form, that says solid. And solid things stay together. And that's just going to be copper all by itself. And then I make aluminum chloride, and that's aqueous in solution. So that's going to form aluminum ions and 3 chloride ions. Now, I didn't really balance this equation, right? But we can see that the chloride doesn't change its oxidation number from one side to the other. What we can see is that the aluminum was solid, meaning that it has an oxidation of 0 and goes to a +3 charge. A 0 to a +3 is more positive, which means, just like cation ions, right? Cats get lost. And so a 0 oxidation to a positive number oxidation means it lost electrons. And lose electrons means oxidation. So that's being oxidized. The copper went from a +2 to copper solid, which would be the 0. A +2 to a 0 means its charge got reduced. It had to gain electrons. Its charge went down, right? It went from a +2 to a 0. And so we call that copper is getting reduced there, okay? And so that is our redox reaction. Then our last type is our acid-base reactions. In an acid-base reaction, we have a proton transfer. So when a proton gets transferred, one compound loses an H ion and hydrogen ion. That's called the acid. It's our proton donor. And another compound gains that hydrogen. So it's a base. It's still going to look like a double replacement reaction, just like precipitation. But you can tell precipitation separately from an acid base, because in a precipitation you form a solid precipitate, but in a acid-base reaction you form water, right? You form that liquid water right there. So that's how we know that we have an acid-base reaction, a neutralization. And let's write the net ionic for this acid-base reaction. So for this acid-base reaction, we've got hydrochloric acid. That says AQ. Anything that says AQ gets dissociated in solution. So we're going to have hydrogen ions and chloride ions. The sodium hydroxide also says AQ. And so that means I'm going to have sodium ions and hydroxide ions. Remember that the OH is covalently bonded, and that hydroxide stays together. Okay, don't separate out the O from the H. Then I'm going to form NaCl is also aqueous in solution, but water isn't aqueous in solution. It's a liquid, so it's going to stay together. My spectator ions in an acid base then are the chloride and the sodium. That leaves me with my net ionic of hydrogen ions plus hydroxide ions form water. When I form water, think acid bases, okay? So now what I would like you to do is look at your handout 4.6a and try to match those 3 reactions with the particle diagrams A, B, and C. And we'll come back together in just a moment.